Welcome. This project is about the efficiency of allocating resources for shutting off valves to allow water main repairs and for new construction to occur. DC Water has one of the oldest water distribution systems in America, and as a result, the number of necessary repairs is growing over time. The process for coordinating valve shutoffs is complex, and so there's a growing backlog. This project reviews the valve shutoff process and determines how to improve it based on the discrete event simulation with a decision support team. DC Water is the water utility company that covers the entirety of Washington, D.C., a 725 square mile area. They serve 681,000 residential customers a year and have over 1,300 miles of pipe and over 44,000 valves. Due to the aging infrastructure, DC Water tries to replace 1% of their piping per year. Valve shuts are when valves are closed to prevent the flow of water through a section of pipe to allow for work in and around the pipe. Valve shuts are often requested for the repair and replacement of the water distribution infrastructure, for construction or new development work, or for regular maintenance, or any other reason that a external stakeholder would need water stopped to an area. Within DC Water, the Distribution and Control Branch, the DCB, are in charge of completing valve shuts. The two important divisions here is Operations Control, which consists of a manager and asset technicians, which create shut plans, which are then followed on by the Valve Division, which consists of the foreman who schedules work and tasks for daily completion, and the crews that actually carry out the tasks at the job site. The process with which a valve shutoff occurs starts with a valve shut request coming in to Operations Control. Then a shut plan is made and is handed off to the Valve Division, where they get any more information that they need and then send out a crew for assessment to mark the street and mark where the pipes and valves are. Then the next day, they will send a crew out to notify ratepayers that their water will be shut off for a period of time. And within 48 hours, the crew will go out and test shut, so shutting off the water for a short period of time and immediately having water sent back through to make sure the shut will hold. Then, depending on the pipe size, Operations Control will need to get a safety clearance if the pipe is over 20 inches, and that will take time. Then they modify the shut plan if needed, and then the plan goes back to the Valve Division, where they notify ratepayers again. Within 48 hours, they go out and complete the actual shut, and then on the next shift of the valve crews, they go out and recharge the pipes, which means they send water back through it, and then the work order is complete. After receiving data from DC Water, we were able to complete a breakdown of the work orders completed. We noticed that 52% of work orders are not assigned to any sort of priority in the internal priority system. Additionally, of work orders with scheduled start and actual finish dates, 67% of work orders experience delays. Furthermore, only 4.1% of work orders have a scheduled start date actually recorded, and then 41.2% of work orders with no dates are assumed to be part of the backlog. This was out of 15,292 total work orders. Furthermore, with 8 total crews working, the Valve Division foreman says that he expects that each crew is scheduled 2 to 3 tasks per day. But according to the data that we had, the current average is 12 tasks per day, or 1.5 tasks per crew per day. We have a large standard deviation, and there is a large right tail, because there are days where the amount of work orders closed in one day is impossibly high. This creates a gap between what is expected of the valve crews and where they are actually performing. Our problem statements are that there is a large number of work orders that are soon to be backlogged, which is growing every month, and the crews are not meeting the work order closure expectation. So there is a need to reduce the backlog of work orders by 33% and a need to increase the average number of work orders completed per day by each crew to be no less than 2. Our design alternatives are to increase daytime crews, which would increase the total number of crews scheduled during the daytime shift from 6 to 8, to reduce scheduling time, which would reduce the lag time in the morning from 60 minutes to 20 minutes before crews can go out on their daily work, and a combination of the two, which would increase both crews from 6 to 8 and reduce the scheduling time from 60 minutes to 20 minutes. To help pick the best design alternative, we decided to build a decision support tool for valve shuts, or DSTVS. The objectives are that it shall be used by the Operations Program Manager at DCB, and shall evaluate the impact of budgeting and staffing changes, changes to the process, operational policy changes, and trends in valve shut requests. Here we have our concept of operations for the DSTVS, which would take work orders for valve shutoffs as an input and output daily work order status reports, daily backlog reports, and yearly summary reports, and is controlled by the valve shutoff policy and procedure and workflow, as well as the staff that would be working within the system. Here we have the DSTVS requirements, which detail information about the outputs of the system, the inter-arrival rates for work orders, and what the user can change within the simulation. Here, we have the simulation model, which mirrors the high-level valve shutoff process. Notice how some of the blocks, such as making shutoff plans and the time between assessment and notifying customers, are set time periods, while jobs such as notifying the customers or recharge are distributed. Here, we have the inter-arrival times for the different work order types. And here, we have the parameters for the staff and crew to show how much they could do on each shift. Notice the equation at the bottom, as that is the maximum that they would be able to do during a day. And here, we have the simulation design UML for the baseline simulation. The DSTVS is a Java-based discrete event simulation model and has just over 900 lines of code in our Java simulation. After verifying and validating our system, our results showed that DC Water has a growing backlog of almost 2 tasks per day over the year 2017 to 2018. This is our design of experiment, where you can see we compare Experiment 1, increasing the number of daytime crews, Experiment 2, reducing scheduling time, and Experiment 3, doing both Experiment 1 and 2, can be compared to the baseline with our simulation results seen on the right-hand side of the screen. Notice the yellow highlighting that shows the difference from the baseline, and that in Experiment 3, both the same changes in Experiment 2 and 1 are made. I will now go further into the results of the simulation. By reducing the scheduling time, the average crew utilization saw an increase by 8.25% in the amount of work orders completed per day, going from 3.0 to 3.25. Here we see a histogram of the size of the backlog of the baseline in experiments 1, 2, and 3. And from experiment 1, the backlog was reduced by 45% from the baseline. Experiment 2 reduced the backlog by 16%, and experiment 3 reduced the backlog by 64%. Looking at the duration time, we can see too that experiment 1 reduced the total duration time, or how long it takes to go from a work order entering the system and being completed out. Experiment 1 reduced that time by 42%, experiment 2 by 16%, and experiment 3 by 59%. To help quantify our recommendations, we created a value hierarchy and utility function where we weighted the 3 properties that we simulated, and using their results can give better recommendations on what to do. Our backlog reduction was weighted at 0.648, and our crew utilization was weighted at 0.23, and our duration was weighted at 0.112. And all of these were scaled from the maximum possible value to the minimum, as you can see on the left of the screen. At the bottom of the screen, we see the utility function, which is the weights multiplied by their results, creating a linear utility function. Using our value hierarchy, we are able to create our utility analysis, where we can see that experiment 3, which is increasing the crews and reducing scheduling time together, had the most utility at 0.610, And experiment 3 will always have the most utility because it is the sum of experiment 1 and experiment 2. Second, we have experiment 1, which is hiring more crews, and that has a utility of 0.389, and then reducing scheduling time has a utility of 0.196. Comparing the cost to utility, the cost of completing experiment 1 and experiment 3 is very high, at somewhere between $480,000 within the first year to $520,000 within the first year. The cost of experiment 3 is the sum of cost of experiment 1 and 2. Meanwhile, experiment 2 has a very low cost because it is only going to cost around $40,000 a year for a new asset management tool, license, and training within the first year, and that would cost around $40,000. As you can see, there's a great gap between the cost of experiment 2 and the cost of experiment 1 and 3. So while experiment 2 doesn't have as much utility as experiment 1 or experiment 3, its cost is significantly cheaper. So our recommendations to DC Water are, first, DCB might consider increasing the number of staff since they are experiencing severe understaffing issues with the crews. Second, the foreman might consider adopting other scheduling methods such as scheduling aid softwares or offsetting work hours to optimize crew utilization. And third, DCB might consider maintaining their operational records and documents. This will help improve the accuracy of the DSTVS, as well as potentially set up the infrastructure to reduce the number of valve test shuts necessary, reducing the overall duration. The reason why our first and second recommendations are separate, even though experiment 3, the combination of the two, had the highest utility, is because of the large cost it would take to hire 2 more work crews. So, if DC Water were to take the second recommendation, it would not meet the requirement of reducing the backlog by 33%, but it would offer some utility for a much less cost than hiring 2 new crews. If we were to turn this project into a viable business, the problem we'd be solving would be inefficient productivity and backlog for water utility companies, and our primary customers would be the maintenance departments and those managers in large water utility companies. Using our simulation results in the system engineering process, we would be giving recommendations to change the maintenance process to increase productivity, reduce inefficiencies, and reduce costs. In the United States, the water utility company market is $113 billion, and there are 404 water utility companies that are comparable to DC Water, and that would be our primary market. A lot of these companies are concentrated on the coast and along the Mississippi River. One of the biggest things that would separate us from our competitors would be the fact that we offer custom solutions, and we wouldn't just be another tool for these water utility companies to use, but we would be around for creating these recommendations and helping with implement them as well. Our company would earn revenue by contracting our team out to these large water utility companies to help create these recommendations and then implement them as well. On average, our contracts would be 19 weeks, and they would earn $208,000 in revenue. Our initial investment would be about $17,000 for 6 months of office space and company technology and supplies. Our monthly cost would be around $30,000 for salary, rent, and other office supplies in our cloud storage. Yearly costs also include travel and accommodations and taxes and benefits. In our simulation for our business plan, at 10 years, our total revenue would be $4.6 million, giving us a profit of $1.3 million and an ROI of 430% in the 10th year. Our break-even would occur after the second week of the second project, which on average occurs in the 5th month of work. Our year-over-year penetration is small due to our team size, and it would be around 1%. Thank you for learning about our presentation, and I really hope you learned something today.